Hess's law is a way that we calculate enthalpy for a chemical reaction. Up until this point, we've been given the delta H for the whole reaction. And now we're going to basically take steps to see how they got that number. How did they find the delta H for the reaction? And so what this Hess's law says is that the change in enthalpy for a reaction is the same regardless of if the reaction takes place in one step, like we've seen thus far, or if it takes place in multiple steps. Okay? There's going to be basically delta H values for multiple steps of the reaction, and we're going to manipulate those reactions and those numbers to get us to our final product. And so I know that seems abstract right now. That's okay. It's basically like a big puzzle we're solving, right? So if you really like puzzles, you're really going to like this lesson. If you're not so big on puzzles, this could be a little bit difficult. Okay? Not difficult, just different. So the good news that with Hess's law is that there's only one correct answer. There's just a lot of steps you could take to get there. There's no set pattern like there is with stoichiometry, right? You have to problem solve to get to the final answer. So get into a problem-solving mindset. This isn't a step-by-step, I'm going to give you everything mindset. This is, we have to problem solve together, basically. Okay? Does that make sense? Okay. Here we go. So you're just going to look, I'm just going to show you this one first. You don't have to write this one down. I just want to walk you through this right now. I'm going to show you what happens, okay? It says, here's our reaction. Here's our reaction. This is what we've seen so far. Nitrogen gas plus oxygen gas yields 2NO2, and this is the delta H of the reaction. This is what we've seen so far. We practiced problems with this. But what we didn't see is how they came up with 68. Right? How did they know it was 68? Okay? And so we're going to dive like halfway into that. Okay? H1 or delta H, yeah, sorry.
What is that formula? Like, is it
this one right here?
the original one? Yeah.
This one? Or this one? Delta H, that tells us how much the enthalpy changed in the reaction. So delta H is the change in enthalpy. And enthalpy is basically the total amount of energy. It's the heat plus whatever work goes in. Okay? Enthalpy is total amount of energy. So the change in enthalpy for this reaction is 68 kilojoules. And it's positive, which means what's happening? Heat's going in, right? They're gaining energy. So H1 or delta H is the total overall reaction. I'll still mostly just label it as delta H. I usually don't put in the 1. Your book does that, but I think it's a little unnecessary. So I'll leave delta H as just regular delta H, but it means it's for the reaction. It says this reaction also can be carried out in 2 distinct steps. Nitrogen plus oxygen yields NO, and then NO plus more oxygen yields NO2. So basically, it's got to take place in 2 steps to get to here. We just don't see that in our overall reaction. Okay? So what they did was they said, if this ends up as our first step, this is the delta H for that step of our reaction. It produces, or it brings in 180 kilojoules worth of energy. The second step of our reaction, on the flip side, releases energy. So we have to find the balance between them. What's the overall or the net between them? Okay? So let's walk through what they're doing here. Okay? We know that our overall reaction needs to look like this. N2, O2O2, and 2NO2. Okay? So we are going to look at our reactions here, our step reactions, and try to figure out, can we make the reaction look like this one? Okay, I know this seems really crazy right now, but we'll get there, okay? So I know that I need an N2 in my final reaction, and I have one right here, right? And it's on the right side, it's on the reactant side, and I need it to be on the reactant side. That's good, right? Yeah. Okay, I need 2 O2s. I have 2 of those, right, which gives me 2 O2s, that's good. And I have a 2NO2. So I have everything that I need. But I also have 2NO and 2NO. One of them's on the reactant side and one of them's on the product side. So what do you think happens? Cancel. They cancel. And so now I'm left with exactly what I want. 1 mole of N2 plus 2 moles of O2 plus 2 moles of NO2. Right? I've got my reactions, or my half reactions, my step reactions, I don't know what to call those, mini reactions. I've got them in the right order. They're at the right size, right? They have the right mole ratios. And so this matches exactly what I need it to be. Does that make sense? Yes, Lauren?
So we have to make the mini reactions?
You don't have to make the mini reactions. Good question. They're going to give you mini reactions that look just like that. The thing that we might have to do, which we didn't have to do here, is we might have to reverse them if our products and our reactants aren't on the right side. We might have to multiply them to be bigger. Like if we needed 2 moles of N2, we would have maybe had to multiply that whole reaction times 2. And so we're going to work through some problems where we have to manipulate it like that. Okay, this one right now, our first one is nice and easy. So we've canceled 2NO, and we're left with exactly what we need. So now we can just add together our delta H values. We didn't have to manipulate our reactions at all. We're just going to add these together. So 180 minus 112 gets us 68. So that's where that number came from. So our goal for Hess's law problems is to manipulate our mini reactions to make it look like our final reaction. And in this one, we didn't have to manipulate, right? But I wanted you to see what the big picture looks like. We cancel things that are on the left and the right, or the products and the reactant side that we don't need in our final reaction. Okay? I know it's totally different. I know it's abstract, but we're going to get there.
So basically just like find pieces of the original equation and then cross out the ones that were there.
That's right. We're looking for, this is what we need, right? I needed 1 mole of N2 on the reactant side. And here it was. So that's great. But if this reaction had looked the opposite, right? If they gave us the mini reaction, and I'm just showing you what would happen here. If they gave us the mini reaction that said this, 2NO yields N2 plus O2, if this is what they had given us instead of that, we would have had to reverse this reaction to get it to look like we want it to. Right? If they would have given it to us like this, it has N2 on the product side, which is not what we want, right? So we would have flipped the reaction, and when that happens, we flip the sign of the H value, and we'll talk through that in a little bit. Okay? All right. Are we feel ready to try one now? I showed you the overall picture, and now it's just problem solving. Okay, are we ready? I know, it's crazy. I know it's difficult. We can do this. All right, so here we go. This is a little more of an overview of what we did here, okay? We said our first mini reaction, H2, took in this much energy. Our second reaction took out that much energy, so our overall was 68 kilojoules, right? We're just finding the net of those 2 little mini reactions as our overall, okay? This can going to talk a little bit about Hess's law.
Separate steps. Step 1 is the combustion of graphite to carbon dioxide. Step 2 is the decomposition of carbon dioxide to carbon monoxide. The net result is obtained by adding the 2 steps and canceling out like terms. The enthalpy change for step 1 is negative 787.
Okay, this is too much for us. Okay. We're going to walk through a little slower than that. This is the rules we have to follow when we manipulate our mini reactions. When we manipulate our mini reaction, if we reverse our reaction, we have to reverse the sign of the H value they gave us for that mini reaction. Right? If we reverse the reaction, we have to reverse the sign. That's really important. Okay? Second step, you can scale way down in terms of what you write. So we can say if the mini reaction, this is an abbreviation for reaction, our XN is the abbreviation for reaction. If the mini reaction is multiplied, then delta H must be multiplied by the same number. Okay? So let's say if our mini reaction gave us O2 and we needed 2 O2, we multiply the whole reaction by 2 and we have to multiply delta H by 2. Okay, so it's however we manipulate the reaction, the mini reaction, we have to manipulate the H value by the same thing. That's what we're looking at. Right? However we manipulate the mini reaction, we have to manipulate delta H that same way. Okay, are we ready? Okay, we're going to start with the easy one.
When you say reverse the sign, when it positive or negative.
That's right. That's right. So if we flip it, we make our products our reactants, then if it was positive, it becomes negative. If it's negative, it becomes positive. Yeah. We'll work it together. So this is the reaction that we want right here. So we want to find delta H for this overall reaction. Okay, that's what we're looking for. But we have two mini reactions that help us get to that point. Yeah, you can just say CG for graphite or CD for diamond, right? That you don't have to write out the whole word. That's up to you. And you don't even really have to include the solid. That's just in there but if you want to, you're welcome to. But we do need to know that we want our final reaction to go from graphite to diamond.
So you write it off?
You can, or you could just put a little G for graphite. It doesn't matter. But graphite carbon is just different than diamond carbon, right? There's energy that has to be either put in or taken out. So Hess's law problems, I will warn you, just require some space on your paper. So just keep that in mind. Or at least I think to stay organized, they require space on your paper. All right, are we ready to start? I don't want to go before we're ready, so, okay. As you solve Hess's law problems, although it's a lot of writing, I think it's important that when you rewrite an equation, if you manipulate one of your mini reactions, you rewrite the other one too, right? So just to keep yourself organized. If you can find a system that works for you, that's great. But I'll just kind of show you what I do as I work through them. These problems, it's just really important that you stay organized and you know where your current mini reactions are at, right? Have they been manipulated or have they not? So we're just going to pay attention to that. Okay, we need graphite on the left and we need diamond on the right. So our first mini reaction, does it have the reactant that we need? Yeah, so this one is fine. It can stay for right now, right? It might not always stay, but it's going to stay for now. Our second one, what do we know we're going to have to do for sure? We know we're going to have to reverse it, okay? So I'm going to rewrite it. I'm going to give me some space up at the top here, and I'll rewrite it. Okay, so I'm going to reverse. I'm going to go ahead and rewrite my first one also, just so I know they're both there. So I'm going to write C graphite plus O2 yields CO2. And my delta H for that first mini reaction is negative 394. So all I'm doing is rewriting that first one. My second one, I know I'm going to reverse it. I like to write a little R to remind myself that I reversed the reaction. That's just me, and that's my method. That doesn't have to be you. But I like to write the R to show me, yes, I reversed it. I did something to it. Okay, so then that would lead us to C CO2 yields C diamond plus O2. And that means our delta H value for the second mini reaction is what? Positive 396. And I like to write the positive so I know I didn't just forget the sign, I was intentional with the positive. Okay? So just make sure you're thinking about those things as you go. Okay? I also, one more thing to help me keep organized, I like to put the yield sign in the same spot throughout my mini reactions. So if I had put it, like really close, oops, that's not what I meant. If I had put it really close to CO2 and then kept going with my products, I sometimes get confused about which side they're on. So I like to just make sure that my arrows are kind of in line with each other. So I know for sure where my products and my reactants are. But that's just me. Okay, so now I've got 1 mole of graphite carbon, which is what I want. 1 mole of diamond carbon, which is what I want. So can my other things cancel? I have 1 mole of O2 and 1 mole of O2. And I have 1 mole of CO2 and 1 mole of CO2. So that gives me graphite yields diamond. And so now to find delta H, I just add those two together. And I get positive 2 kilojoules. Of oxygen, there's 1 on the reactant side and 1 on the product side, so they cancel. And then CO2 also had 1 on the product side and 1 on the reactant side.
So for the mini reactions, will we always be given their delta?
Exactly, yes. You will always be given delta H for the mini reactions. Something else to think about is that when I cancel my O2s, I only can cancel the amount of moles that can cancel. Does that make sense? Since these were both 1 mole, they canceled. But if I had 2 moles here and 1 mole here, I would have only been able to cancel this down to 1 mole. Right? Does that make sense? It's like reducing a fraction. If they're the same, they cancel totally. But otherwise, you just have to be careful about the mole ratio with those. Okay? It's most of the time always going to work out. Always it's going to work out to what we need. But sometimes it just might take multiple steps. So this was a relatively easy one. We just had to reverse 1 reaction, but you do have to be careful with the sign. Well, these are mini reactions. Remember, we're going to get them to whole number ratios. This is what we want to get to. We don't want to get to the fractions. We want to get to here. This is what we need. Here's our mini reactions.
Would you multiply by 2 over 2?
We'll get there. To get a half to a whole number, you'd multiply it by 2.
Yeah.
Right? So then we do the whole thing.
What would you multiply 2 by to get rid of the
You could multiply it by 2 to get rid of fractions. Yep, we'll do that. We'll get there. I promise. Okay? Get this written down. Give yourself some space to manipulate. I might put this one at the top of your paper. Sorry, I'm just telling you. I would put this one at the top and then put the mini reactions under. That way you can have room to manipulate them underneath without running into your real one. Sorry. I should have put that better on the slide.
They're so weird. My dad's like, just give them a
All right, I'm going to rewrite the reaction we want at the top so that I have room to move underneath.
Do we need to put like a fixed G or whatever?
No. Mm-mm.
Would this be easier if the fractions were decimals?
Nope.
Okay.
So will we always be solving for delta?
Yes. This is the reaction we want. I just erased it.
Yeah, but how come the second mini reaction doesn't even have nitrogen?
Well, we're going to have it from here, right? It doesn't have to be in both reactions. It's just got to be somewhere.
Do we ever have we have to have a mini reaction?
No. No, we'll always be given the mini reactions.
Okay, so we won't have one.
Where did the
No.
reaction?
No.
Where did the mini reactions come from? Did they just any?
Yeah, that just means this reaction might take 2 steps to get there, but we don't ever look at that in depth.
Where do they come from?
Smarter scientists than me figure that out.
put them down.
Yeah, I mean, they just realized that in order to get to those two products, we have to do it in 2 steps.
So
this will be
this is like just like a calculation.
Not
of
the
something
quiz, but the
that
test.
moves.
What'd you say?
This is like a calculation of something that someone did.
Yeah. Yeah. Okay, are we ready? All right, let's start. Let's start. Okay, so let's look at our first mini reaction. Are my things on the right sides? My first reaction is NH3. Do I want it to be on the reactant side or the product side? NH3, do I want it to be on the products or the reactant side? Look, see, I want NH3 over here, and I want N2 over here. So I need to reverse this, right? I'm going to put a little reverse arrow, and then I'm going to come down here and rewrite it. So I reversed my reaction, which gives me 1/2 N2 plus 3/2 H2 yields NH3. And so the delta H for that reaction is now what? Negative 46. Okay? My second mini reaction, is it on the right side? Do I have things on the right side? No, I don't, because I need water to be on the left, so I need to reverse that one also. So my second one now becomes 2H2O yields.
Reverse the original equation. Reversing both of them.
Yes, but you'd have to remember to reverse your H at the end.
Yeah.
So yes, but that's not the way it's ever taught, so I'm going to keep going with this one. Okay, good question. That's okay. Plus O2. So my delta H for that reaction now becomes positive 484. Okay, so we've got the products and the reactants on the correct sides. Now we've got to get the mole ratios where we want them to be. Okay? So how many moles of N2 do I need? 2. So what do I need to multiply this reaction by to get this to it to a 2? If I multiply it by 2, that gives me a 1. If I take 2 times, so I need to multiply it by 4. So I multiply it by 4. I have to do that for the whole reaction, and I need to do that times my H. So I'm gonna come down here. I'm gonna make another line, and I'm gonna rewrite them again down below. Okay, you want me to do it in a different color? Will that help? Okay, so that gives me 2N2 plus how many? Right? 12 over 2H2 gives me 6H2. Okay, is everyone on the same page with how we got that? 3/2 times 4 is 6. Yields how many NH3? 4 in.
Not do the subscript.
No, it doesn't. It's just about coefficients. Good question. It just multiplies the coefficients. We don't adjust subscripts at all. Good question. Okay, so now we take delta H is now 4 times negative 46.
184.
So negative 184. Okay, so how do we feel about that? Okay, so far?
Wait, so we just multiply the top one?
We only multiplied the top one right now. Now we've got this, we've got this, we've got this. We've got to find 3O2 somewhere, okay? So what do we need to do to this reaction? Multiply it by 3. Oops. I'm silly. We don't have the water. We don't have the water yet. Thank you. Okay, we need to multiply this reaction times 3. That gives me 6H2O yields 6H2 plus 6O2. Sorry. That's fine. I was wrong. You can't see it written down there. I'm sorry. Yes, you are right. 3O2. Can you see what that's supposed to be?
6H2
yields 6H2 plus 3O2, and that means my delta H value is 484 times 3, which is
1452.
yes. And is it positive or negative? Positive.
It's gotta be positive, yeah.
Oh.
Sorry, we started with it negative and we reversed it, so it's positive 14. Sorry, I can't move that icon, but it should be positive 1482. Okay, so now let's see, can we start canceling?
Yeah.
What can I cancel?
H2, 6H2.
Okay, and then I'm left with 2N2 plus 6H2O. So yes, yes, and I'm left with 4NH3 plus 3O2. Yes, yes. So now I add these two together. Negative 184 plus 1452